what I wanted to quickly go through is I put these slides in. I just wanted to quickly go over how our reaction rate, sort of how our graphs work, and how you can sort of manipulate these graphs. So as you can see here, I'm going to go through 1, 2, 3, 4, 5, 6, 7, 8. There are 9 slides on these, and we're just going to go through them in a couple of minutes. We're not going to spend too much time. But essentially what we've got is we're going to have different equations, and what we're going to do is we're going to add or take away or divide or remove or add in something different. We're going to go over all the different ones or add a catalyst or whatever is going on. And these are concentration time, and then we'll also look at rate time. So in this case here, we've added a product or reactant, either one. What have we done here? We've added a reactant, sorry. We've added N2 gas, because you can see here, we're at equilibrium all the way up until here. So all the way up until here, we're at equilibrium. Then all of a sudden, we added some N2 gas. As you can see, there's this little spike here. We added some N2 gas. Essentially, when that N2 gas was added, we were out of equilibrium. We needed to get back to equilibrium. By doing so, we needed to reduce our N2. We needed to increase our NH3, because by reducing it, we're going to go forward. We're also then going to inadvertently reduce our H2. Now, how do we know how much we're reducing or increasing by? Now, these shouldn't have been subtext, sorry. How do we know how much we're increasing or reducing by? Well, the first thing I want to say to all of you is that draw an imaginary line here. This N2 should never go below this line. It should never touch that line. It should always be above it, because you've added more to this system. So when it reaches equilibrium, there needs to be more of this still. So when it reaches back at equilibrium, this needs to be more. So essentially, you've gone up and then you're going to come back down. Now, there is a 1 out the front here, there is a 3, there is a 2. So however much of this goes down by, however much you decide to draw it down by, which you can draw it down as much as you want or as little as you want, as long as it doesn't touch this line or get near it, doesn't matter. That area there, for NH3, I'm going to double it. So treat this like maybe like 1 centimeter. This is going to be a 2 centimeter rise. For my H2, this is going to be a 3 centimeter reduction. Because as the reaction went forward, this one goes down, this one goes down, this one goes up. You need to make sure you use the constants as your factors by how much things go up and down. For this one, it went down by 1 centimeter, so therefore this one needs to go up by double that. So this was 1 centimeter, this needs to go up by 2. This one here was 3, so it needs to go up by 3 times that. Think of it like molar ratios, same sort of thing. That's what we're working with here. And then we reached a new equilibrium where this blue line was. For our forward and back reaction, what you'll find is if something is added, there is more concentration in there. So what's going to happen? The rate overall is going to be quicker, but we're still going to be at equilibrium. So we've just reached a new equilibrium here, and essentially think of these lines on top of each other at the same rate. But essentially right here, we've reached equilibrium again. And this equilibrium just has a slightly higher dynamic pace. The pace of the dynamic sort of forward and back is just a little bit higher. Now I know those are terrible lines, but essentially think of it like that. And what went up, the forward or the back reaction the most? Well, the forward reaction went up the most, first of all, because if we think about it, we needed more of our NH3 initially, so our forward reaction is the one that's going to go up quickly. Now, again, sorry for the subtext, I don't know why I did that. But essentially, this one went forward first, and then this one went sort of increased as this one went down with it. So in this system, initially at equilibrium, and then we get the addition of N2, and then the equilibrium established again. Cool. Now, what if we dilute something? So we're not going to remove something, now we're going to look at diluting. What if we diluted this whole thing? What if we just added water in and diluted this whole thing down? Well, what actually happens is everything decreases. The concentration of everything decreases. Because remember, concentration is moles over liters. And if we dilute something all the way down, we're still going to have the same number of moles, but we're going to have an increased number of liters. So think about it as moles. Oh, I don't want that second line there. The moles is going to be constant, and then the liquid is going to increase. So therefore, your number is going to decrease overall. So your concentration is going to decrease. So think of it like this. That kind of stance of concentration. So overall, you get a concentration decrease for all three of them. However, as you notice, two of them then went up and one of them went down. How do I justify that? The way of justifying this is looking at the number of molecules on each side. So on this side, there is 1, 2. There is 2 on the left and there is 1 on the right. Despite the fact this molecule is probably a little bit bigger in size, doesn't matter. You've got 2 on the left, 1 on the right. How do I overall increase my my concentration of everything within there? How do I get back to a point where I'm happy? How do I do that? Well, what do is I actually go to the left. And again, we worked on ratios. Everything was of the same ratio here. So this was the same distance as this, was the same as distance as this. All these distances were the same. And essentially what you've got here is this concentration increasing for both SCN and Fe3+, because there's 2 of them on the left and there's 1 on the right, so this one's going to decrease. So we're going to push back to the left. Now, what if for theory's sake, there was a 2 here and I had 2 here? I know that doesn't make any sense because it's not right, but just for theory's sake, well, in this case here, you would actually go like this. You'd go, all right, get down to here, and then I'm just going to go straight. I'm not actually going to get a change. Nothing's going to change because there's no ability to change. For this one's just going to go straight. For this one is just going to go straight. They're just going to go straight. It's at equilibrium. When it reaches this point here, we're at equilibrium still, if these are 2 and 2. And again, for our dilution with our rate, it goes down, it goes the opposite. And then, as you can see here, we wanted to increase our SCN and Fe3+. So this one stayed higher initially, and this one reduced initially because we didn't want as much FeSN2. Now, what if we change pressure? So what have we done here? Have we increased or decreased the pressure? We've increased the pressure because we've got more concentration. So our liquid, if we think about it, or our space, our volume, has decreased in this one. Again, these should not be subtext. I think that was just the way I typed it out. Apologies. But essentially, that is what's going on here. So everything is increased. So because everything is increased, what do we want to do as a system? We want to decrease. So here, I've got 1, 2, I have 3 particles on the left. I have 2 on the right. So which one has less? It's the SO3. So we're going to go forwards. So the SO3 has increased. As you can see here, we have a space there that is, as you can see here, is about, it's about equal to this. It's probably not perfectly equal, but these two here are meant to be equal, and then this one is going to be half of it. But essentially for the production of these graphs on PowerPoint, they weren't perfect. Now, moving on, again, change in pressure, everything's going to increase, but we want to get more SO3, so our forward reaction is going to increase more. Change in temperature, there's no immediate change. Now, this is why K value changes, because in all of these ones, we have an immediate change, and then we work our way back. So during this phase here, we have a Q value, and then we work our way back to a K value that is the same. Temperature, we have a Q value, from here to here, we have a Q value, then we work our way to a different K value. This is a different K value because we've had a change in temperature, and temperature is the only thing that will change the K value. Super important. So, 2NO2 gas can come back to or go to N2O4 gas, and as you can see here, we've had a temperature change, and with that temperature change, I'm going to say we've added heat. For the sake of it, we've increased the temperature. By increasing the temperature, what we've done is we've increased the amount of NO2 and we've decreased the amount of N2O4. So we've increased the back reaction. What does that tell me about this equation? That tells me this equation is exothermic. Now, how do I know that? We would have a negative delta H. And again, how do I know that? Because when I add the temperature, I want to cool the system down. So how do we cool the system down? Well, we cool the system down by going backwards, because this side would be the hot side, because when we go through an exothermic reaction, remember with like combustion, exothermic, we get a lot of heat getting produced. When we go through an endothermic reaction, so let's say this was endothermic, this would get cooler. because it's absorbing energy into the system, but essentially that energy is it's making it cooler. So I think of this as the hot side. I think of this as the cold side. So we want to go towards the cold side, so we're going to go backwards. Now, if this had been an endothermic reaction, it's the opposite. This would be the cold side. I'm just going to say Y and X, and then this would be the hot side. So this is, I'll write it out nicely. So, and then I say delta H equals, I'll make that negative. So let's just get rid of all these scribbles over here so I don't confuse people. And I'm going to say Y X delta H equals positive. What I've got is I've got cold and I've got cold. And then I have hot and I have hot. So depending on what you do, if you reduce the temperature or increase the temperature, you're going to go to the opposite. And that's how I know what's going on here. Now, important here, for this one here, we've said, what have we done with the temperature? We've actually reduced the temperature. Otherwise, you can also increase the temperature. Now, also the other really important one is catalyst. Catalyst really important if it was a concentration time graph, so concentration time, and you had two things, and then all of a sudden you added a catalyst in here, it would still look like this. Nothing's going to change. You're not going to increase, that shouldn't have gone up. It looks terrible. You know what I mean? Nothing's going to change. That was terrible. Let me redo that one. Nothing's going to change. They're going to stay the same. And when you add a catalyst, the only thing that's going to change is a rate graph. It's going to go up, but then it's going to stay the same. You're always going to be at equilibrium. So again, we have another practice question here where we've only got about 50 minutes left, a little bit less. So what I'm actually going to do is skip over this practice question. I do apologize. Again, I've actually quoted in this one this time. Apologies. I've given you part A, which is the information you need. Please have a go at this question and then go to the exam and have a look at it. So for those of you at home, welcome to pause and have a go at it now. For those of you watching the premiere, please come back to this question afterwards. It's slide 52. And please have a go at it there. So that might be a good way of doing that. So, block 2.